Hello, my name is Dr. Richard Griffin. I'm a faculty member at Texas A&M University, and for the next 2 hours we're going to have a whirlwind tour through the material science subject. I've put my phone number, fax number, and email down here, and I understand that we will have an opportunity to have questions in a couple of weeks together. I hope you have a chance before the question set time to read through the notes. In addition, I would really encourage you to work through some of the practice problems, get a feel for what types of questions that the fundamental exam asks. A 2-hour session is no comparison with individual preparation. The handout that you have consists of a number of pages related to what we're going to talk about today, and I've put a table of contents in there. The first topic that we're going to talk about will be corrosion, and then if you want to know where the different topics are, those are the pages. To begin our discussion, we're going to zoom in a little bit, and I've put 3 pages in the notes that are called metals hierarchy, polymers, and plastics. And this is really for your information. If you look at metals, there's 2 classic conditions for metals. One is ferrous alloys, and that would include steels, alloy steels, cast irons, and then non-ferrous materials, the light alloys, aluminum and copper, the conductors, copper and aluminum. So the metals are typically categorized into ferrous and non-ferrous alloys. Now polymers, which are far more complicated in some sense, are broken into 3 typical subsets. That's thermoplastic materials, thermoset materials, and then what are called natural rubber materials. The thermoset and the thermoplastic materials have far more industrial applications than the natural rubber materials. The thermoplastics are materials like polyethylene that our milk is contained in. The thermoset materials would be like the epoxies, the glue that holds our club heads onto our golf shafts. And then the final category of materials that I have here would be ceramic materials, and while relatively low in volume compared to metals, there are some very important ceramic applications. Glass, of course, most of us look through glass either driving our car or out of our automobile. Many insulators are made from glass materials, electrical insulators. And then there's some interesting engineering ceramics related to the high-temperature gas turbine engine. The ceramics are similar to the polymers, can be both crystalline, which we'll talk about in a minute, and either glassy or amorphous. Now, to get to the business of the discussion, we're going to take a few minutes and talk about corrosion. There are 3 requirements for aqueous corrosion, and these will be listed here. The first requirement is that you have a potential difference. And that potential difference means that you're going to develop an anode and you're going to develop a cathode. So if we have a solution here, we're going to have an anode and we're going to have a cathode. The second thing that you need is an electrolyte. And an electrolyte is a solution that contains ions. For example, seawater is a marvelous electrolyte. Engine oil, at least fresh engine oil, is not an electrolyte. There are not supposed to be ions there. My car, it's another situation. So we have an electrolyte in there, and then the third thing that we need is a connecting path between the anode and the cathode. Now, we actually have learned 3 ways to stop corrosion. We could break the connecting path, we could we could remove the solution or keep it dry, and we can avoid the potential difference. Now, this shows a separate anode and cathode, and we know that if we leave a hammer out overnight in the warm, damp air, in the morning there will be some rust on it. So if we have an electrolyte, let's call it seawater, and if we put a piece of iron or steel in that electrolyte, then there will develop on there local anodes and cathodes so that the connecting path is within the metal. Now, there are both anodic and cathodic reactions. The anodic reactions are really easy. There's only one reaction that you have to learn, and that reaction is the oxidation reaction. So if we have some metal and it goes to some metal with a particular valence, we're going to get that many electrons. This reaction is called oxidation. The oxidation reaction gives up electrons. Now let's do a couple of examples here. If we take iron, iron goes to 2 plus 2 electrons. And maybe some of you remember that iron also has a 3-valent or a trivalent material. That's called ferric. This is ferrous. But the ferrous is the most common valence that you have. If we take a look at aluminum, for example, aluminum is trivalent, and there would be 3 electrons. So the anodic reaction, the only one you have to know is the oxidation reaction. Now, the cathodic reaction, on the other hand, has several different reactions, and we're going to take a look at 3 of them. The cathodic reaction is where reduction takes place, and reduction involves the consumption of electrons. Now, there's an interesting fact associated with corrosion, and that is that the net oxidation must equal the net reduction. So the electrons that are produced must be consumed. We've learned another way to slow the corrosion process, and that is to slow either one of those reactions so that the electrons are either not produced or not consumed as easily, and that will slow the corrosion reaction. The first reaction is hydrogen reduction, and if we have H plus an electron, that goes to H2. Often you see it with a little arrow indicating that it's going to be a gas. Now, to balance that, we need 2 electrons and 2 hydrogen. You can also write that with the hydronium ion, the H3O plus. This is the reaction in acid solutions. And remember what the definition of an acid solution is. The pH, which is a measurement of the hydrogen ion concentration, must be less than 7. So something like hydrochloric or nitric acid would be, at a pH of 1 or 2, would be a very, very strong acid. Now, one of the elements that is a major problem with corrosion is oxygen. And there are 2 oxygen reactions. One for an acid solution, so the pH has to be less than what? Well, we just said it, didn't we? has to be less than 7. The oxygen reduction reaction is oxygen plus 4 hydrogens plus 4 electrons forms 2 H2O. So oxygen in the presence of an acid solution is a corrosion reaction. Power plants often are very careful of boiler feed water to control the oxygen content. We've learned another way to control the corrosion process, and that is to eliminate one of the chemical species. Remove the oxygen can be a way to slow or stop the corrosion process. Well, those two are acid solutions. Let's look at the reduction reaction that occurs in basic or neutral solutions. And so now the pH is going to be equal to or greater than 7. And we're going to be concerned about hydroxide ion concentration. A material that is basic in nature is seawater. Open ocean seawater has a pH approximately 8. And areas like Galveston Bay that have a large influx of fresh water under times of heavy rain can drop down to 7.4, and it can go as high as 8.4. The oxygen reduction reaction in basic or neutral solution has oxygen plus water plus 4 electrons going to 4 hydroxide ions, and let's see, we need a 2 in there to make the equation balanced. These 3 cathodic reactions cover almost all of the corrosion situations. The anodic reaction is no problem. The cathodic reaction usually is one of these 3 reactions. Let's work a little example and see how we might do this. Consider nickel in seawater. So I like to draw a little picture of myself. Put a piece of nickel in there. And this is seawater. pH is about 8. So the anodic reaction would be what? Well, we need to know what the valence of nickel is, and we can look at a periodic table or the EMF series that's in the handbook that you want to take to the EIT exam, and you want to work with that handbook a little bit so you know where stuff is. You get to the day of the test and you're under pressure and you won't be able to find what you want. So that's the cathodic reaction. I'm sorry, the anodic reaction. The cathodic reaction would be, let's see, this is a basic or neutral solution, so the cathodic reaction that we would like to have would be this one right here. So we could write the cathodic reaction as oxygen plus 2 H2O plus 4 electrons going to 4 OH. Now to balance this, we only have 2 electrons here, so we've got to multiply this by 2. We can add these, and so the overall reaction would be 2 nickel plus oxygen plus 2 H2O goes to 2 Ni2 plus 4 OH. And the hydroxide often will precipitate, so it would certainly be okay to write this in the following way: NiOH2 with 2 of those. Often the hydroxides will precipitate. Well, that's an example, and you might fool with the acid solution ones, and if you have a question on that, when we meet together and talk on the questions, I can respond to that. Well, let's take a look at the table the EMF table on page 61 of the Fundamental Exam Handbook, and that's terrific right there. Two things I'd like you to be aware of. If you look at the bottom down here, you see sodium, magnesium, and potassium, and that tells you active. If you go up to the top, you see gold and platinum, and you see noble, inert, not active. So if you have to make a choice in a solution, if there's a couple of materials, take for example chromium and silver for some reason are in contact, which one's going to be the anode? You look at this table, this region's going to be anode, this region is going to be the cathode. So the active ones will tend to be on this particular table at the bottom. Sometimes the tables get flipped. Just keep in mind you see sodium, potassium active, gold, platinum, you know those are going to be inert. So these are going to be more noble in this direction. Now this EMF table is under equilibrium conditions, and there's another chart which is sometimes used, and that would be the galvanic series, where the galvanic series actually lists alloys. But this EMF chart is a good first start if you're trying to decide what would be the anode and what would be the cathode. How you might develop anodes and cathodes. And in addition to having materials of different chemical composition, you can also develop an anode and a cathode with respect to materials because of what has been done to those materials. For example, cold worked material will be anodic with respect to annealed material. Grain boundaries will be anodic with respect to the matrix of the grains. A second phase particles with respect to the matrix. Now those two can flip, but the point is that if you have differences, you can end up with an anode and cathode. Oxygen concentration. High oxygen concentration regions will be cathodic with respect to lower concentration, lower concentrations. Where can you get that? Well, in solutions. If you only have a solution like a seawater on an offshore platform, if you have soil and a structure in the soil, it's not uncommon to have oxygen concentrations. And similarly, solution concentrations can do the same thing. If you have a solution concentrations that's high on one part, lower on the other part, it will be, the high side will be cathodic, the low concentration will be anodic. So there's a variety of different ways that you can develop anodes and cathodes. And let's see, I guess the last one that I have here is compositional. Differences. So if you have an alloy that has local compositional differences which might occur from the casting process or some operation, those can lead to anodes and cathodes. Well, that completes the discussion on corrosion, and now we should be on page 8 of the notes, and we're going to talk about bonding. There are 3 types of primary bonding: metallic bonding, ionic bonding, and covalent bonding, and one type that's called secondary bonding, van der Waals, or hydrogen bonding. And while van der Waals is much weaker, it still is important. It holds liquid water together by the hydrogen bonding, and then it's a secondary form of bonding in polymers, and also is important. Now, metallic bonding is for metals. There's a couple of characteristics of metallic bonding. You might consider cores of ions, and if it's a univalent material like lithium or sodium, each one of these is going to have an electron associated with it, and people talk about the electron cloud or the electron gas. And this form of bonding leads to a couple of characteristics. Metallic bonding typically are ductile, fortunately for us, for cars and structures. They typically have high conductivity, and that would be both electrical and thermal. Metallic structures on the can also be strong and can have from low to relatively high melting points. They are tough, and they can be formed. One of the words that is used is malleable. Now, a downside of the metallic structure is that most metals would rather be oxides. So they are relatively easy for corrosion to occur, and so we work hard to protect metals from the environment. There is a picture of metallic bonding on page 9 of the notes, and it suggests the little picture that I showed you a minute ago, where you have cores with electrons. On average, if it's a univalent or single valent material, one electron will be associated with each ion, each positive core. The second type of bonding, which is very important, is ionic bonding. The classical case of ionically bonded materials would be sodium chloride. Ionically bonded materials are from opposite ends of the periodic table. We mix electropositive materials with electronegative materials. Sodium, for example, would be electropositive. Chlorine would be electronegative. So sodium gives up its electron and becomes positive. Chlorine is real happy to take that electron. It completes its outer shell, and you have a very strong bond. Some characteristics of ionically bonded materials would be that they typically are brittle, high melting points. They cleave, similar to a diamond. They break along particular crystalline phases, and they are insulators. And that would be both electrical and thermal. Also, ionic materials typically are salty to the taste. Those of you that are into French fries know how good salt is. Another type of bonding is covalent, and for many materials, there's a mixture of both ionic and covalent materials. The covalent bond involves shared electrons, and perhaps a classic example, we might take a look at methane that has a central carbon atom, and it bonds with 4 hydrogen atoms. So methane would be CH4. The electron would be shared between the hydrogen. So part of the time hydrogen has 2 and it's happy. Part of the time carbon has 8 electrons, fills the outer shell, and it's happy. These bonds are very strong. We would have very high melting point materials. We have the hardest material in covalently bonded, that would be diamond. High melting points. They are hard, they are brittle, and they are insulators. Now this is an interesting category. All of them are electrical insulators, and most are thermal insulators. And we might just put a little footnote to ourselves there, because diamond is a wonderful thermal conductor, but and very good electrical insulator. So there are thinking about some thin film applications where you use diamond in various devices to get the heat away, but provide the electrical insulation. But most covalent materials are both electrical and thermal insulators. And finally, and there's a picture of ionic and covalent bonded on page 10 of the notes. The final type of bonding would be secondary bonding. The van der Waals, this is weak, low melting points. In fact, the rare gases, argon, neon, which become liquids at very low temperatures, are held together with van der Waals forces. But it is the force that holds water together, and it's the secondary bonding in, plan ahead, the secondary bonding in polymers. And I have a little picture of that I would like to show you. This picture corresponds to PVC, polyvinyl chloride. Much of our outdoor drainage pipe is made from PVC material. And if we look at the chain here, within the chain, those are covalently bonded. Carbon-hydrogen bonds, covalent, very strong, and the chlorine atom that's in there. However, between the chains, as designated by these plus and minus regions, these little polar regions, there is a weak attraction. Now, in polymers, the molecules are very long relative to metals and ionic and ceramic materials. And so lots of little secondary bonding can contribute to the strengthening characteristics. So individually it's negligible, sum total it makes a contribution to the mechanical behavior of polymeric materials. The next category that we're going to talk about will be crystallography. And to start on crystallography, we'd like to do the following. We're going to talk a little bit about crystallography, and before we do that, I think it's worthwhile to define what you mean by crystal planes. And this is done in terms of Miller indices, and we'll work a couple of examples here. And I would recommend that you might practice on some of these on your own. Now, with the little units that I have here, we'll put the origin at the back. Maybe we can blow this up a little bit. make it a little easier to see. And there's nothing magical about where you set the origin. What you want to do is just make it easy on yourself. Now, Miller indices look formidable, but they're really simple. And I'll show you right here. What's the value of Miller indices? Well, if you're going to talk about a particular kind of crystal plane, then the numbering system is true for all the planes. The unit dimensions of the cell may change, but the particular plane would be the same for any of them. Let's consider this plane right here. Oh, and I guess we should define our axes. I'm going to let X come out towards us, Y here, and Z will come out the top. Now, with the Miller indices, the first thing you need to do is get the intercepts. What are the intercepts for this plane? Well, it doesn't look like it intersects X, and it doesn't look like it intercepts Z, but it intercepts Y at 1. So we can put our y-intercept down there as 1. Now what about z and x? Well, the plane is parallel in the sense that it goes up and covers through 3 dimensions. And where do parallel lines intersect? Well, parallel lines intersect at infinity. So the intercept would be infinity, 1, and infinity. Now the next thing that you have to do, and this is maybe the trick, you take 1 over the intercepts. And those of you that are fast already can see what's going to happen. We've got 1 over infinity, 1 over 1, 1 over infinity. So the Miller indices will be 0, 1, 0, and for a particular plane they represent that with parentheses. So the Miller indices for this particular plane would be 0, 1, 0. And if we took a look at this plane right up here, we could do the same thing and we'd see that this was a 0, 0, 1 plane. Now that represents the individual plane. If you want to represent a that's individual. If you want to represent a family of planes, that's represented with these braces. So this would correspond to a family of planes. And if you had a family of 1, 0, 0 planes, that would include the 1, 0, 0, the 0, 1, 0, 0, 0, 1, bar 1, which would be in the negative direction, 0, etc. So it would include all those individual planes. Let's try a little more complicated one, okay? Let's take the diagonal plane and let's use this diagonal plane right here. Now you see that it goes through the origin, and that poses a problem for Miller indices. If the plane goes through the origin, either move the plane or move the origin. All right? So in my head, I'm going to move this origin to translate this origin to this point right here. And if we want the intercepts for that plane, those intercepts are going to be what now? -1. Sorry, we don't need 2 x's. -1, 1. Now it's going to be, the origin's out here, it's going to be parallel to z again, so it's going to be infinity. So we want to take 1 over the intercepts, so that's going to be 1 over -1, 1 over 1, 1 over infinity, and that's called bar 1, 1, 0. So this plane would be the bar 1, 1, 0 plane. And let's try one more. And I would encourage you just to fool around and practice with these a little bit. There's some examples in the handbook there. So X Y, Z, and let's do this plane right here. Now the intercepts for that plane are going to be what? Well, it's going to be 1 in the X, half in the Y, and then 1 in the Z. So we're going to take 1 over the intercepts, so that's going to be 1 over 1, 1 over half, 1 over 1, and so the Miller indices for that plane would be 1, 2, 1. Okay? So I hope you have a little sense of how you might determine the Miller indices. And they are very important, actually, when you talk about slip processes, cold working of material. Now, and these Miller indices are designated H, K, L. So the 1, 2, 1, H would be 1, K would be 2, L would be 1. Now the directions are really the easiest of them because they're like vectors. You just read head to tail. If you don't have it going through the origin, you subtract head from the tail and you can get the vectors and you read the vectors off directly. But let's try a couple here. We'll use the same coordinate system, X, Y, and Z. We'll put the origin back, and let's try this direction right here. So the direction is 0 in the X, 1 in the Y, 0 in the Z direction. And directions are indicated with brackets. That would be an individual direction. Families of directions are indicated with these caret marks. Generally, you write the family as the 1, 0, 0, and that would correspond to a family of directions, meaning all directions of this type. 1, 0, 0, 0, 1, 0, 0, 0, 1, bar 1, 0, 0, etc. Let's try this direction right here. That's supposed to be the cube diagonal, so it intercepts at 1, 1, 1. That would be the 1, 1, 1 direction. Now for cubic systems, the direction, the normal to the plane, has the same Miller indices as the plane. So a 1, 1, 1 direction is going to be perpendicular to a 1, 1, 1 plane. This 0, 1, 0 direction that I have down here is going to be perpendicular to this 0, 1, 0 plane. That works for cubic systems. And let's try one more. Let's try one that only comes out to the half position there. So the direction would be half, 0, 0. Okay, the intercepts would be half, 0, 0. You clear of fractions, and this would be the 1, 0, 0. Directions are always reduced to their lowest common denominator. Let's try one more. If we put a direction in a position like that, we would have 0 on the X, we would have 1 on the Y, half on the Z. We clear a fraction, so we would have 0 to 1. That would be the 0 to 1 direction. Well, we're going to switch over and talk particularly about crystallography right now, and we're going to start with the body-centered cubic. And I would suggest as we go through this, if you're in a position where you can stop this tape, as we go from one page to the other, before I do some of the things, you might just try them and practice them yourself, and then you could look at the tape and see if you got it right. There's 3 crystal structures that you're responsible for: body-centered cubic, face-centered cubic, and hexagonal close-packed. And in looking at some of the questions, they do variations of those. We're going to look at 3 things. We're going to locate the atoms. We're going to determine the number of atoms per unit cell. We're going to determine the coordination number and the packing factor. And I'll show you how to do the density also. Now let's look at body-centered cubic. We're on page 13 of the handout. And body-centered cubic is just like it sounds. There's an atom at the center, and then there's an atom at each corner of the unit cell. What's the unit cell? This is the simplest part of a lattice that can be reproducible in space. So this is the bottom line of the lattice. We can extend this throughout space and end up with iron, vanadium, tantalum, tungsten, are all body-centered cubic materials. Let's determine the number of atoms per unit cell. All right? Well, this is pretty easy. The center atom, 1. That's inside the unit cell. Now there's 8 corner atoms, but not all of the corner atoms are actually included. And if you make yourself a little XYZ axis here and think about that as being 8 quadrants, there's only 1/8 of each of the corner atoms within a unit cell, so that's going to be equal to 1. So the body-centered cubic unit cell has 2 atoms per unit cell. Now, supposing you would like to know what the radius of one of the atoms are. Well, this is a cubic system, and A is defined as the lattice parameter, or the unit cell dimension. And the atoms touch along the cube diagonal. It doesn't show in my picture, but that would be called a close packed direction, in that the atoms touch. And let's say we would like to try to determine what the radius of these atoms are, remembering that we're trying to take a real nucleus with electron cloud around it, and we're saying that we can represent this with a hard sphere model. Well, this is the way we could do this. We will call this distance x, and we know from Pythagorean's theorem that x squared is equal to a squared plus a squared plus a squared, so that x squared is equal to 3a squared. Now x is equal to 4 times the radius of the atoms. 1, 2, 3, 4. So we can substitute in there for x 4r squared plus 3a squared. I think I forgot the equal sign in there. And if we solve that for r, we can have r squared is equal to 3a squared over 16. If we solve for r, it's going to be a over 4 times the square root of 3. So if we can measure the lattice parameter, we can get a handle on what the radius of the atoms are. Now, what's the coordination number? Well, if we look at the body-centered atom here for the coordination number, how many atoms are in contact with it? 1, 2, 3, 4 on top, 1, 2, 3, and if you'll accept the imaginary one back there, 4 down here. So the coordination number for body-centered cubic is 8. So each atom has 8 nearest neighbors. Now that's more near neighbors than we'd like to have, but each atom has 8 nearest neighbors. Now what about the packing factor? The packing factor, PF, or sometimes you see it as phi, is equal to the volume occupied over the total volume. And if we work that out, the total volume is A cubed. The volume occupied by atoms is going to be equal to what? 4/3 pi r cubed times what? How many atoms per unit cell? Well, hopefully you're saying 2. And we know from the relationship up here what to substitute in for r. And if you work this out, the packing factor will become 0.68. Well, let's try it for face-centered cubic material. We can do the same. You might go ahead and give a try at drawing the face-centered cubic before I do it and see how you do. The name is a giveaway. There is an atom in each face, and then 8 atoms, 1 at each corner. The close packed direction is the face diagonal. The unit cell dimension is A. Fortunately, it's a cubic, so the volume is equal to A cubed. And we can determine the radius of the atoms, again using the assumption that the hard sphere model works. This time it's a little bit easier. We can say, if we call this distance x now, we can say x squared is equal to a squared plus a squared, because we're using the face diagonal rather than the cube diagonal. Again, though, there's 1, 2, 3, 4 radiuses in there, so we can say x is equal to 4r. 4r squared is equal to 2a squared. R squared is equal to 2a squared over 16, and r will be equal to a over 4 times the square root of 2. So if we know the lattice parameter, we can estimate what the size is. Now, how many atoms per unit cell? This is a fun activity. Students go from 7 to 17 on this one. Let's try the corner atoms. We can do those first. There are 8 corner atoms. And remember, from the body-centered cubic, how many are located within each unit cell? That would be 1/8, so we would have 1 atom associated with the 8 corner atoms. Now, what about the 6 face atoms? Okay, well, if you look at this face right here, how much is in this unit cell? I hope you're saying half. So we've got half is in each unit cell, and we would have 3 atoms, or for a total of 4 atoms per unit cell for the face-centered cubic material. Now, this is called a close packed structure, and this and the next one, hexagonal close packed, are both close packed structures. So it has a higher coordination number than the body-centered cubic. Now, close packed structure means that it's made up of close packed planes. Might go ahead and draw one of these close packed planes on your notes there. I've got one a couple pages back. You see that for this close packed plane, let's look at this atom right here. How many nearest neighbors does it have? 1, 2, 3, 4, 5, 6 nearest neighbors. So in 2 dimensions it has 6 nearest neighbors. But now if we took another one of these close packed planes and put it on top, we could have 1, 2, 3 atoms more in contact above the plane, 3 atoms more below the plane. So the coordination number is 12 for face-centered cubic. Each atom has 12 nearest neighbors, and that's typical of a close packed structure. We can look in here also and see close packed directions. This is called a close packed plane, and each close packed plane has some number of close packed directions. How many do you think it has? What's a close packed direction? That's one where the atoms are going to be in contact, so it looks like we might have 1, 2, 3. So each close packed plane has 3 close packed directions within it. And the close packed plane for face-centered cubic corresponds to the cube diagonal plane, or the 1, 1, 1 plane, and then the close packed directions are the face diagonals, so this particular plane has 3 close packed directions, which I have represented with those little dotted lines. Now this is a close packed structure. It has a coordination number of 12, so it should have a little higher packing factor than the body-centered cubic. And if we look at the packing factor for face-centered cubic, it's going to be equal to the volume occupied by atoms over the total volume. So the volume occupied, let's see, that'd be 4/3 pi r cubed. Now, how many atoms per unit cell? There, hope you're saying it. 4 divided by a cubed. And we know that r is equal to a over 4 square root of 2. If we substitute that in there, this will work out to be 0.74. And that's the highest packing density for a close packed structure. Now the other crystal structure that was in the workbook, or the booklet that you can take to the test, is the hexagonal close packed, and there's a couple ways you can represent this. This is called the large unit cells, what they have. And if you can think about it as being a hexagon, and we're going to put a close packed plane, we can designate that close packed plane as an A layer. If we go back a minute to the close packed structure of the face-centered cubic, the way this is stacking sequence, because both face-centered and hexagonal close packed are both made up of close packed planes. This is stacked A, B, C, etc. You tip it on an edge and you can end up with that cube. However, the hexagonal close packed is stacked a little bit differently. It is stacked at AB on through space. So this particular plane is called a basal plane, and its Miller indices are 0, 0, 1, and it has 3 close packed directions. The unit cell can be represented by this hexagonal close packed structure. There are 3 atoms located in the middle, which I'll try to put with a little X in there, and then there's another close packed plane on top. The unit cell dimensions are A, and now we need a second dimension C, because it's no longer cubic, and this is the easiest of both of them. A is equal to 2r, r is equal to a over 2. And if they're perfect spheres, the A over C ratio, or C over A ratio, is 1.63. Now how many atoms per unit cell? Well, there's 3 inside, That's going to be 3. We have 6 corner atoms below, 6 corner atoms above, so that would be 12. And they're in 12 corners. They're in 1/6 of a unit cell, so there's 2 of those. And then we have 2 face atoms, face center atoms. They're each in 1/2, so there are 6 atoms per unit cell. There is another unit cell which we won't fool with, which is a little bit simpler. It's a rhombus. The coordination number, well, it's a close packed structure. That's easy, isn't it? Coordination number is 12. Packing factor, this is a close packed structure. The packing factor is going to be, if they're perfect spheres, is going to be the same as face-centered cubic, and that would be 0.74. Now we can calculate the density actually, so that using the unit cell and the atomic structure, we can actually calculate what the bulk density would be, and this is called the theoretical density. Density, rho, is equal to mass divided by the unit volume, and we'll call this theoretical density here. And let's do this for face-centered cubic material. So that's going to be equal to what? The atomic weight divided by Avogadro's number times the number of atoms per unit cell divided by the volume of the unit cell. So 4 is the number of atoms per unit cell. N0 is Avogadro's number, and this is the atomic weight of the material that you were interested in. You might try that for nickel and then compare it to the value that you get by looking up in the handbook. Now I've already done this, but just to reiterate here, and this density, when I say the theoretical density, this has every atom on a lattice site. And not all atoms are on lattice sites. They have vacancies or impurities in there. So this would have the highest density. If we take a look at a close packed plane and a close packed structure, close packed plane has, each atom has 6 nearest neighbors. There are 3 close packed directions, close packed direction, and then this corresponds to a close packed plane. In face-centered cubic, it's the 1-1-1 plane. In hexagonal close packing, it's a 0-0-1 plane. And in the body-centered cubic, there are no close packed planes. There are some almost close packed planes, but there are no close packed planes. That'd be the close packed direction, close packed plane. Now the close packed direction in face-centered cubic is going to be the face diagonal, so it would be 1-1-0. In the hexagonal close packed, it's 1-1-bar-2-0. And in the body-centered cubic, the close packed direction is the 1-1-1 direction. So that would be the close packed direction. These are the close packed planes. The next area that we're going to talk about will be diffusion. We're going to talk about diffusion, and diffusion is one of a group of processes that are called thermally activated processes. Diffusion is important in the semiconductor industry, in the metals industry. Actually, it's important in the bottled pop industry. You don't like to buy a bottle that has all the fizz that's gone out of it. And I'd like to make a couple of comments. If we could go to the screen and enlarge it a little bit there. and talk a little bit about a thermally activated process. When a process is thermally activated, it suggests that it follows a Boltzmann's distribution, and it says that the rate is proportional to a e to the minus energy over RT, where Q here is called the activation energy. R is the gas constant. That's usually the number that you don't have the right conversion factor for. And T is the temperature in Kelvin. The gas constant R is 1.98 calories per mole degree Kelvin if the activation energy is in calories per mole. But the important thing is that for a thermally activated process, somebody tells you it's a thermally activated process, you can write the equation down in terms of the rate immediately. It's the rate proportional e to the minus activation energy over RT. And this crops up in lots of different areas. It's important in diffusion, which we're going to talk about. It's also important in creep, and it's important in the semiconductor industry. It's also important in the annealing process, which we'll talk a little bit later about. Now, just to make a comment on the thermally activated process, if you go to the second page, page 18 here, suggesting atom movements, you will see that if an atom is in this position right here, and in order to climb up here, it has to have this much energy called Q, where Q is the activation energy. If any of you have ever sled or lived where it's been cold or cross-country skied, you know the joy, the difficulty of getting up to the top of the hill. Well, what a thrill coming down. So this activation energy is the energy you need to climb up the hill. Once you get the hill to the top of the hill, it just falls on down. As temperature increases, the activation, it becomes easier for the process to go. It's exponential, so it's going to be a very significant function of the temperature. Now for diffusion, if we can take a look at that diffusion equation there a little bit, please. For diffusion, we can write that the diffusion coefficient D is equal to D0 e to the minus Q over RT, where D0 is called the pre-exponential term, and really it has everything in there that we don't know. D here is the diffusion coefficient. Now, supposing you'd like to calculate Q, how can you do that? Well, if a Boltzmann distribution satisfies, and you can apply this thermally activated process, which is called the Arrhenius equation, then you can solve for Q in the following way. If we write that D is equal to D0 e to the minus Q over RT, and we take the log of this, we have log D is equal to the log of D0, and if you take the log of the E, then the exponent comes out. You have minus Q over RT. And this should look amazingly like the equation of a straight line, where B is log D0 and M is the slope minus Q over R. So if on the log of rate, in this case diffusion versus 1 over T, if it's a straight line, this slope is equal to minus Q over R. So we can obtain the activation energy. Temperature here is in reciprocal Kelvin. Now there's two types of diffusion. One is called vacancy diffusion, and the second type is called interstitial diffusion. And in the little two-dimension picture that I have on page 17, we can represent a vacancy diffusion. If we can imagine that this is a lattice and we're only looking at 2 dimensions, then there is an empty lattice site. So if this atom moves to that lattice site, then we'll make the vacancy as represented by a square set of dashed lines, then the vacancy moves here. So if the atom goes to the right, then the vacancy will move to the left. And in order for the diffusion process to happen, 2 things have to be there. The activation energy here is going to be equal to the energy to form a mole of vacancy plus the energy for an atom to jump. So this is to form 1 mole of vacancies, and this is the energy to jump. So in order for an atom to diffuse in vacancy diffusion, you have to have an empty lattice site, and then the atom has to jump into that site, and then the vacancy goes the other direction. Now the second type of diffusion also can be categorized as volume diffusion, is interstitial diffusion. Now interstitial elements are small atoms that sit between lattice sites. And I've tried to represent this by this atom right here. So if we can think of this as a 2-dimensional one, this little interstitial atom fits in between. Now there's only a relatively few number of atoms that are interstitial. Carbon, hydrogen, carbon, oxygen, nitrogen, and boron. Those are basically the interstitial atoms because they have to be small in diameter. They don't sit on a lattice site but in between lattice site. Now the difference for the activation energy here is that Q is only equal to the energy to jump. You do not need a vacancy. So there's no vacancy needed. And fortunately, both types of diffusion can be described by the as a thermally activated process or an Arrhenius equation, and D is equal to D0 e to the minus Q over RT. Works for both vacancy and interstitial diffusion. Now I wanted to mention the vacancy and interstitial diffusion for the following reason. If you go to page 20 of the handout, you'll see a table that lists diffusion coefficients for a number of materials, both metal systems and ionic or covalently bonded materials. If you look over here at the top, you'll see hydrogen, carbon in various forms of iron, and you'll see the slope is relatively shallow. The diffusion coefficient are very high. Interstitial diffusion, it has a lower activation energy because all it needs is the energy to jump that does not need a vacancy. For iron in itself, or this is substitutional diffusion or vacancy diffusion, and you'll see that the slope is much greater, and that's because we now need, in addition to the energy to jump, we have to form a mole of vacancies. And if we go over here to calcium in calcium oxide, This is an ionically bonded material. Now you've got charges to be concerned with, and the activation energy is going to be even higher. And carbon in graphite has a very high activation energy. So we can say something about the relative magnitudes of the activation energies because of what we know about their diffusion. Interstitial diffusion, relatively easy. Substitutional or vacancy diffusion, a bit more difficult because you have to have vacancies. And in ionic covalently bonded materials, we're going to have to break bonds, and in ionic be concerned about charge, which makes diffusion more difficult. Well, the next area that we're going to cover is phase diagrams, and there are two systems that are shown in the handbook. One is a eutectic system and one is a eutectoid system. The eutectoid system is represented by the iron-carbon system and is probably, industrially speaking, the most important. I can't emphasize enough that if you're uncomfortable with this, you just need to practice a little bit. These are easy. It just takes a little bit of getting used to the terminology. The phase diagram that's shown on page 21 represents a eutectic system. There's a number of industrially important eutectic systems. The lead-tin system, which would be the basis for solder, would be one important one, and aluminum silicon, which is used as a cast alloy in a variety of different parts. Hand grips for bicycles, sometimes lightweight parts of the suspension system. Let's work through this diagram and talk a little bit about what some of the different phase fields are and what they mean. You would start out with the melting point of, in this case we're talking about A and B, but it could be aluminum, it could be silicon. And then as you add one element to another, in this particular end of the diagram, we're adding B to A. So A would be called the solvent, and B would be called the solute. And as we add B to A, we find that there is a lowering of the melting point, and this phase boundary is called the liquidus. That phase boundary separates the solid from the liquid. Now there's a second phase boundary down here, and that phase boundary is called the solidus. Almost off the page, sorry. That would be called the solidus. This horizontal here is called the eutectic, and the word eutectic can be frustrating because there are a couple of different applications of the same word. This reaction point right here is also called the eutectic and represents a reaction where you have liquid going to alpha plus beta. So you have a liquid going to solid 1 plus solid 2. And that'll be very important here in just a minute. Now, we can talk about the Gibbs phase rule, which can help us identify what goes on in this system. The Gibbs phase rule is defined as the number of phases plus the degrees of freedom is equal to the number of components plus 2. And for solids, pressure can generally be ignored, And the Gibbs phase rule can be written as the degrees of freedom is equal to the components minus the phases plus 1. So P is the phases, C are the components. That's usually the minimum number of elements that are required to specify the system. Phase is a homogeneous distinct region. And F is the degrees of freedom. And generally, you can ignore pressure for solids, so we can write this as the degrees of freedom equal the components minus the phases plus 1. Let's take a look at this eutectic point. So the number of degrees of freedom is going to be equal to components. Well, that's 2, A and B. And minus the phases. How many phases exist at the eutectic point? Well, we just wrote this reaction right up here. 1, 2, 3 minus 3 phases plus 1. That says that the degrees of freedom are equal to 0. Well, what's that mean? Let's have the eutectic point is at a composition of looks like it's at 5A, so about 60% there. If we have an alloy that has a composition of the eutectic, and we plot temperature versus time, and we're cooling on down to some temperature, let's say this is 100, 200, 300, 400, 500 degrees centigrade. When we get to 300 degrees centigrade, then that temperature will stay constant, because in this region there are how many degrees of freedom? 0. That means you can't vary composition or temperature. We've already said pressure is not going to vary. And then when it's completely solidified, it will start to cool off. So here we have liquid. This is going to be solid. And that solid is going to consist of alpha plus beta. Now this is the same thing that happens when ice solidifies. You've got liquid, you're cooling it down, it gets to the freezing point and stays there until all of the ice is solidified. That's because it has 0 degrees of freedom. Let's try a little example up here. So in the liquid range, how many degrees of freedom? We can write it F is equal to C minus P plus 1. We have 2 components. How many phases? Well, there's just 1 liquid plus 1, so we would have 2 degrees of freedom. And that means that we could change composition, or we could change temperature, and there would be no change in the phases. So that's what it means to have 2 degrees of freedom. Let's try one more. Let's go over here into this region right here and try it. So over in this 2-phase region of beta plus liquid, we're going to have the number of degrees of freedom is equal to the components minus the phases plus 1. 2 components, how many phases? Let's see, beta plus liquid minus 2 plus 1. So we would have 1 degree of freedom. That means that if we change composition, temperature's fixed. If we change temperature, then composition is fixed. We can't change them both without getting out of that phase field. So that's what the number of degrees of freedoms mean. Now there's 2 important things that, in addition to a phase diagram, you want to be able to identify the composition of an alloy, okay? And you want to be able to determine how much of an alloy exists there. And let's do two examples, and these are applicable also to the iron-carbon diagram, eutectoid system, that we'll see in just a moment. Let's pick a temperature, and let's say that it's about 320 degrees. We'll go with this dashed line down here, and that looks like about 30%. We'll call that 30%. Now we're sitting at this point. What would the composition of the two phases be? Let me put another sheet of paper on here, and we'll use this. We want to know the compositions, and we want to determine the amounts or relative fraction. When you want to determine the amounts, you have to use the lever rule. When you want to determine the compositions, you just read them from the diagram. So now we have composition. We simply drop a perpendicular down to the composition axis, perpendicular, and read composition. So in this case, let's see, if that's 30%, this looks like it might be maybe 10%. And this one, if this was 60, this looks like maybe it is 55%. So the composition of the liquid would be 55, and this is in weight percent, so 55 weight percent B. Composition of the solid alpha would be a lot less, and it would be 10 weight percent B. Now how can it be 55 and 10 if the overall composition is 30? Well, the B in liquid plus the B in solid alpha must equal the B in the alloy. So if we totaled up the B in the liquid and the B in the solid, it would equal the 30 that we see right there. Well, I hope that's clear. You might fool around with a couple of those. Now let's try determining the relative amounts. How much liquid and how much solid would be in there? Well, to do this, we need to use the lever rule. And the lever rule works in the following way. The fraction of liquid is going to equal the following. You take the length of this is called a tie line. Take the length of your tie line, and the tie line ties the two single phase regions together. So that's going to be 55 minus 10. Then you're going to take one side of the tie line for the liquid and one side for the solid. How do you decide which side? Well, it's sometimes called the inverse lever rule. You take the opposite side. So we decided this was 30, so it's going to be 30 minus 10, and that will be 20 over 45, or 4 over 9. So a little over, the fraction's going to be about 0.4 something. Now, you could be saying, whoa, that looks like magic. How did that guy do that? Well, it's conservation of mass. But if you get confused, and if you go up here, you're just below the liquidus, what are you going to have? Mostly liquid or mostly solid? Well, it was all liquid there, so we're just going to have a little bit of solid and mostly liquid. So the liquid's going to be the big portion over the total. So the liquid's going to be the left-hand side. If you were on this side, it would be the opposite side. So you can always go to a place where you're sure what the concentration is and decide which length of the lever arm it would be. Okay, so now let's determine the fraction of solid. Now a couple of you are ahead of me know that the fraction of the liquid plus the fraction of the solid has to equal what? 1, or percent, has to equal 100. So we could write the solid right away. The fraction of the solid is going to be equal to 1 minus the fraction of the liquid. But let's do it with the lever arm. We take our tie line, 55 minus 10. Now we want to take the other part, which we said was 55 minus 30. And that would be equal to, what, 25 over 45. Oh, yeah, 5/9. So that should be about 0.6. 0.4 plus 0.6 equals 1. Let's try one other calculation, and we'll do this in the two-phase field and then go on to the iron-carbon system. Let's go down to the solid line that is shown on the diagram that we have right here, and we'll use this point right here. Now it's going to be exactly identical to what we did. The two phases that we have are alpha and beta. So we can ask ourselves, composition, alpha and beta. We can just read those right off the diagram, and if we look over here, this x alpha looks what, maybe 7, and x beta looks maybe about the same value, but let's say x beta looks like 92. So the composition of alpha, this is the alpha phase field, is going to be 7 weight percent B. What that says is that up to 7% of B is dissolvable in alpha. What do you mean dissolvable? Well, you take water, add sugar to it. What happens? Shake it up, the water's clear, the sugar's dissolved. Those of you who have made iced tea know that if you add sugar when the iced tea's hot, what happens when you cool? Well, if you put a lot of sugar in, you start to get cloudy. That's because it exceeds the solubility limit, starts precipitating out. So up to 7% at this temperature of B is soluble in A, and the percentage of B is 92 weight percent B, which says that how much A is dissolvable in B? I hope you're saying 8. 8% B is A is dissolvable in A. So that would be the compositions. Let's determine the amounts. And remember, to determine amounts, we got to use the lever rule. And for this calculation, our tie line is going to be 92, 7, and our fulcrum is going to be here at, or the point that we're interested in, it is about 30. So the fraction of alpha is going to be equal to what? Well, we certainly can put the denominator down there without a problem. That's going to be 92 minus 7. And if we look at the fraction of beta, that's going to be 92 minus 7. Now we're a little concerned about the numerator. What are we going to put? Well, if you can remember that it's the opposite side, the alpha is going to be 92 minus 30. Say again, well, how did I know that? Well, you're on the alpha side of the diagram. If you were over here, you know it would be mostly alpha. So it's got to be the bigger portion of the line over the total line. And then the fraction of beta is going to be 30 minus, what did we say that number was? 7. 30 minus 7, so we'd have 62 over 85. and 23 over 85. So looks like on the order of 3/4, on the order of 0.25. So if we were to draw, for example, what the microstructure might look like, what we would find is, this is the microstructure, and let's let it be at 500 times, we would see the majority of this material is going to be alpha, and it's going to account for about 75%. There's going to be beta in here, and the beta is going to be about 25%. Okay? Now there's one other thing that you can do actually here. If you wanted to know how much eutectic and how much alpha, you could draw your line, your tie line, right at the eutectic point, and then the question could be how much eutectic and how much alpha, because we're on the side of the diagram that's called hypo-eutectic. This side of the diagram is called hyper-eutectic, so it would have more than the eutectic composition. Hypo has left. The first phase that comes out of the liquid is alpha. That's called the primary phase. On this side, the first phase that comes out is beta, called the primary phase. So if we wanted to know how much eutectic and how much alpha, then our tie line goes from 7 to the eutectic, which we said was 60, and we're here at 30. So the fraction of alpha is going to be equal to 60 minus 30 over 60 minus 7. The fraction of eutectic is going to be the opposite portion of the lever arm, and that's going to be 30 minus 7 over 60 minus 7. That's going to be 30 over 53, so that's going to be about 0.6. And this is going to be 23 over 53, about 0.4. And what would that tell you then if we were to draw the microstructure? And this is a really cross off that other microstructure that you had here, because if we're going to have 60% alpha, the other product, the eutectic, comes out as an intimate mixture of two phases. So, and it might come out as platelets or something like this. So these crosshatch regions that I have drawn here correspond to what's called the eutectic, and it's an intimate, meaning fine, mixture of alpha and beta. So the alpha in eutectic plus the primary alpha has to equal the total alpha, which we calculated on the previous page. So I really ought to put this thing back up here and really ought to cross this diagram off and remind you that you would have primary alpha, and then this crosshatch region represents a mixture of alpha and beta. Well, I hope that gives you a little bit of an idea how to make some lever rule calculations and how to determine the compositions. Let's go ahead and take a look at the iron-carbon system, because this is probably industrially most important. And there's a couple of additional phase reactions that are useful to know. One is the eutectoid reaction, where you have a solid 1 going to solid 2 plus solid 3. The iron carbon system, this corresponds to gamma or austenite going to alpha plus Fe3C, or iron carbide. And this product has a unique name. It's called perlite. And perlite is a intimate mixture of alpha and iron carbide. Now the paratectic reaction, which an example of is up here, is a reaction that has a there are two particular additional reactions that we might be concerned about. One is called a paratectic reaction, and that has a liquid, in the case of the iron carbide diagram, plus a phase called delta, which is a high temperature form of iron, and that forms gamma or austenite. So that reaction would be up here. The paratectoid reaction is the inverse of the eutectoid reaction, and it has a solid 1 plus solid 2 going to solid 3. And there's no example of a paratectoid reaction in the iron carbon system. Let's take a little look at the iron carbon diagram, because we're going to use it in a minute to talk about heat treatment of steel. From around this region on over, we would have cast irons. This is a eutectic reaction, and this reaction right over here is the eutectoid reaction. Generally, steels have less than 1% carbon. 1040 steel, which would be a plain carbon steel, would have 0.4 weight percent carbon in that particular material. So most of the steels, the regions of interest would be in this portion of the phase diagram. Let's take a look at the two-phase field down here and work a lever rule problem showing with the iron carbon diagram. And let me just expand this a little bit. Now, not very much carbon is soluble in body-centered cubic iron. This is alpha or BCC iron. It's called ferrite. This is gamma. It's face-centered cubic, and it's called austenite. If we add enough nickel and chromium, we can have a stainless steel and have an austenitic stainless steel. This is the eutectoid reaction, and that's at 0.77 weight percent. So, what's this phase field? Alpha plus austenite, and down here we have alpha plus Fe3C, or carbide. And let's take a 1020 steel, so we have 0.2 weight percent carbon, and let's make a couple of calculations. Let's determine the amount of total alpha and total iron carbide. And let's determine the amount of what's called primary alpha and the amount of perlite. Not pearl light, but perlite. Now the amount of alpha in here, we would draw the tie line between, and we need to choose a temperature. This temperature is let me make sure I got the right number here, 727. So just to make this easy on ourselves, let's say it's at, we're at 725. So we can use those phase boundaries. So the total alpha then, the lever arm would go from 0.02. Well, now how far is it going to go over here on the right? Well, Fe3C is 25 atomic percent or 6.67 weight percent carbon. So it would be 6.67, and we're at 0.2. So the total alpha is going to be equal to 6.67 minus 0.02, and then the numerator is going to be 6.67 minus 0.2. And now that's not surprising, as it looks like it should be mostly alpha. The iron carbide is going to be a smaller amount, so it's going to be 0.2 minus 0.02 over the 6.67 minus 0.02. So that'd give us the total alpha and iron carbide. But supposing we wanted to know the alpha that came out first and how much perlite would we have, then our tie line, let me put a little box here, then our tie line is going to go from where? 0.02 to where? Please? 0.77, and we're at 0.2. So the primary alpha is going to be 0.77 minus 0.2 over 0.77 minus 0.02. The amount of perlite would be 0.2 minus 0.02 over 0.7 minus 0.02. And let's see, that'd be 57 or 60 over 80, so it looks like it'd be about 3/4, about 0.75, about 0.25 on that order. And let's just go ahead and draw the microstructure for ourselves so we would have an idea of what the microstructure would look like. Well, we'll do the same thing. We'll call it 500X. And I hope you're a little bit ahead of me and saying, well, gee, this looks like that eutectic system over there, except it's a eutectoid. So we're going to have 75% primary alpha. Alpha is body-centered cubic iron called ferrite. And then 25% of the regions are going to be this perlite. And perlite is an intimate mixture of alpha plus Fe3C. So the total alpha is going to equal what? The primary alpha plus the alpha in perlite. Now in a few minutes we're going to talk about, and you might just try a couple of those calculations. In a few minutes we're going to talk about the heat treatment of steel. And for the heat treatment of steel, if you could put the picture back on, the first step is going to involve forming austenite. So in the heat treatment, we're going to heat above these phase lines, phase boundaries, and into this austenite phase field. We'll quench it, and then when we do the tempering process, we will heat below this line 727, which is called the A1. We're going to talk about thermal processing for just a minute. And the first thing that we're going to talk a little bit about is cold working. in cold working or strain hardening. Now in the mechanics sequence, you've talked about a tensile test, and we'll just touch on it here in a minute. But once you exceed the yield point and the material starts to plastically deform, and when you remove the load there's some permanent deformation, that process is called cold working if it's done at room temperature or less than about a third of the melting point, or strain hardening or work hardening. And if we plot the strength or hardness versus the percent cold working, what we would find is, let's say this is 50, it might increase something like that, probably start to level off. An example of this might be the copper zinc system or the brasses. So as you deform the material, it becomes stronger. Now there's no freed lunch, is there? So if we perhaps put the ductility on this side, and we'll represent the ductility as a dashed line. As the strength increases, what's going to happen to the ductility? Well, the ductility is going to decrease, isn't it? So the ductility might be 60%, and it would go down to a low value. The strength might start out as 30 KSI and increase to on the order of 70 KSI. So as the strength increases, the ductility. Now, is this recoverable? Well, the answer is yes, and the process is called annealing. And annealing involves heating to a temperature generally greater than half to 2/3 of the melting point. Now, why do you want to be greater than half the melting point? Well, an hour ago we talked about diffusion. What kind of process was diffusion? Thermally activated, wasn't it? So the annealing process is a thermally activated process. So the higher the time, the shorter the temperature. So this is a function of time and temperature. You can use high T, short time, low temperature, long time. And the process of annealing involves three stages. Recovery, where stresses are relieved. Recrystallization, where the cold worked strength is lost and ductility returns. And then finally grain growth, where the grains start to grow and you have fully recrystallized grains, and then you can actually go through the cold working process again. And if you look on page 24 for the copper zinc system, you can see the change in hardness and tensile strength as you cold work the material, and correspondingly the decrease in elongation. The recovering process or recrystallization process is shown on the figure on page 25, and for the brass system, you can see that as this is the recrystallization temperature and the amount of cold work, 20, 40, and 60, so this would be stronger, have less ductility, and you see the recovery process occurs a little earlier as the cold work increases. Provides more energy, it's a little easier for the process to get started. And so this would be the recovery, this would be the recrystallization. So this is going to be recovery, this is going to be recrystallization, and this over here is going to be grain growth. This same material could be cold worked again, and the process could be done again. Now there's a way of heat treating materials so that you can change their strength also, and in particular the example that I am giving you here is for steel. We can develop what's called a quenched and tempered microstructure, and the first step in that process is to austenitize or heat. This puts alloying elements in solution. The second stage is to quench. This traps the alloying elements in solution, and in the case of steel, this is very hard and brittle. And then tempering involves a reheating to a temperature less than 727, and now tempering causes the strength to lower or decrease and ductility to increase. So it's possible by a heat treatment to make materials change the microstructure so you can strengthen it by a heat treatment operation. And these strengthening mechanisms are interesting. We can add alloying elements, we can cold work, and we can heat treat. And many of these are additive so that you can combine their effect. We're going to talk about grain size at the end of this discussion a little bit, and the grain size, the finer the grain size, the stronger the material. So there's a variety of ways that you can strengthen a material. If you look on page 27, you will see a heat treatment cycle for a 0.8% steel. This is called a eutectoid steel. You heat it up to 1600, hold it till the alloying elements are in solution, quench it to room temperature, reheat it to 500, hold it, and the phases will redistribute so that they become increase the ductility and still have reasonable strength. In this condition, in what's called martensite, this is an incredibly brittle material, has almost no uses except for some wear applications. It doesn't have much fracture toughness, and very little ductility, very hard. So the tempering operation redistributes the phases so that we have an increased strength, decrease the strength and increase the ductility, but more important, we increase the toughness of the material. Now steels are hardenable. That means that they can be hardened in various size sections depending on the alloying elements. And the way this is described is by a Jominy hardenability curve, and these are offered in the handout on page 64 that you can take into the book, take into the test with you. And I'd like to share a couple things with you in the time that we have remaining. A 1020 steel, can we enlarge that a little bit, please? 1020 steel, which is indicated at the bottom there, corresponds to 0.2 weight % carbon and virtually no other alloying elements, a little bit of manganese. On the other hand, a 4340 steel, of course, is a chrome nickel molybdenum steel and corresponds to about 5% alloying elements. You'll see that the line, this Jominy hardness curve, is very high. 4340 and 4140 would be considered very hardenable steels. 1020 would be considered not a hardenable steel, and you can see by the initial hardness here, it's not one that you would generally heat treat to form martensite. So you need about 0.25 or about 0.3 carbon before they will become fully hardened. As you add alloying elements, the hardenability increases. Well, what can you do with these hardenability curves? I'll give you an example here in a minute. Now the geometry test is interesting. You have a piece of steel. It's about 4 inches long. It's 1 inch in diameter. You austenitize it or heat it in the austenite phase field. You quickly move it and you spray or you put water on this one end. So this is cool. This is hot. It's considered a one-dimensional heat transfer problem. The heat got the arrow going the wrong way. The heat is drawn out of the material, and the geometry curve measures the hardness as you go back from that water-cooled end. So the cooling rates decrease as you go away from the water-cooled end. And if you look at the top of the figure on page 28, you'll see out here the cooling rate is 3 degrees centigrade per second. The cooling rate here is 150 degrees centigrade per second. So it cools much more quickly at near the one end of the bar than the other end. We're going to conclude this tape, and there'll be another few minutes of tape on the next section, and we'll complete this material on the iron-carbon diagrams, precipitation hardening, mechanical properties, grain size, and composite materials. Thank you.